All right, so let's now turn our attention over to the other half of our lecture over here. The other topic in our lecture here is about the squeeze theorem. Right, and so I'm going to use this board to write down the actual squeeze theorem. But now before I get any further into the idea of squeeze theorem, let me get to the other board of mine right here, and I'm going to start out with an introduction problem, a problem that introduced the idea why we need the squeeze theorem. So at this point in our learning, we have learned how to use basic limit laws, and that produce for us a whole bunch of algebra steps so that we can handle the polynomials and we can handle rational function pretty effectively and pretty efficiently. We also learned just earlier in the earlier half of this lecture about how some basic trig function like sine of x and cosine of x and an exponential function. But now function a lot of times become a little more challenging, and none of the techniques I've mentioned just now will be able to help us to handle the problem. So let me introduce a problem like this. Simply, we want to evaluate. Our goal of the problem here is to evaluate the limit of sine of 1 over x. So we got trig function. But now dangerously, inside of this trig function, there's something else. It's not just the simple sine of x. So sine of 1 over x. And then this function sine of 1 over x is actually multiplied with, say, x squared, for example. Okay? And we are asked to find the limit as x is getting close to 0. So definitely we don't want to plug things in. Because plugging things in, first of all, we did not have any algebra or any limit laws that allows us to plugging things in this way, other than just the simple power rules and all the sums and the difference. We don't have any of those categories here. So once again, stay back to the ground. We cannot simply plug this limit point into the function. Because why? What's the worst problem here is that when we substituting that x equals 0 into the function, we got a 0 here, and we got a 1 over 0 inside of our sine function. So things is going to go in all directions. And so in that way, we're going to, here's some observation. Remind yourself again that the function sine of x, any sine function, is known to be greater than or equals to 1 and less than or equal. So sine of x is greater than or equals to negative 1. I should have said that earlier. And then being less than or equal to 1. So this is a very known bound of our famous trig function, sine of x here. But the intention further is that regardless of whichever value of x, then the sine of x is always in between this bound. So we can apply this understanding into our particular function here. No matter what x value is, but sine of 1 over x will be for sure be anywhere inside of that famous bound again. So it's just some thoughts about, I'm starting out a problem completely, it's not let's not worry about a brand new technique or something like that. I'm just trying to trigger your own understanding by, bringing up these previous knowledge of yours prior to this class right here. So doesn't matter where x is at, or whichever value you're substituting in, of course, should be inside the domain. But doesn't matter which value we're substituting in for this function. Sine function is famously known to be anywhere from negative 1 to 1. That's the bottom line. We can't change it. So, but observe a little further. Now, once we have a known bound for this function, if we look back into our ultimate goal here, our function that we were attempting to find the limit here had that sine of 1 over x right here. And this sine of 1 over x already known to have a bound. So we also learned that we can multiply, this is a three-sided inequality, but we can multiply x squared to the middle function to produce x squared times sine of 1 over x. But if we multiply a number to, or some expression to one of the sides of an inequality, then make sure we are multiplying that same expression to the rest. So in this case, to the other two sides as well. So x squared multiplied with -1 gives me a minus x squared. And x squared multiplied with +1 gives me positive x squared. So what I let myself down here is that I now found out that my x squared times sine of 1 over x is being trapped between, I'm not saying bounds anymore, because bounds in usual math terms refer to fixed bound with constant bounds. Like this is a bounds. This is a pair of bounds. But now I'm just simply saying that my function here is being trapped between some two other functions. So this function's x squared times sine of 1 over x is proven just now, proven by inequality that it's greater than or equal to a function, something to this function minus x squared. And then in the meanwhile, this function is proven to be, regardless of whatever x value it is, always less than or equals to x squared. So that's one thing to notice about. And then now another observation, and I need everybody to take note carefully before I can erase this, because I need some more board space for here. And so, or maybe I don't need more board space. What I can do here is that think about this function on the very far left hand side right here, minus x squared. This function minus x squared, then basic limit laws now allows you to quickly find out that this function minus x squared has limit 0 when x is coming close to 0. The same thing with the x squared function on this side of your, on this very other side of your inequality right there. If we're taking limits of this function as x is getting close to 0. Now why did I deal with x coming close to 0? Because the beginning problem was given that x is getting close to 0. That was our beginning limit point problem. It could be some other problem in other, some other limit points in other problem, but here in this problem here, I particularly want to look at the limits when x came to that given limit point. And so now back to this function that I was in the middle of. So x squared here, now if we're letting x getting close to 0, we're going to come out with a limit 0 as well. So, but the role of these two functions, they are what I call them, they are the trapping functions. They trap our x squared times sine of 1 over x in between them. So these two trapping functions, the bottom, the bottom and the upper end right here, they both come to the same limit. They both go to the same limit as we're letting x getting close to that given limit point. And so now my conclusion, ladies and gentlemen, I can actually make a conclusion here that our limit, maybe let me get back to this board right here, but limits of this function x squared times sine of 1 over x will be guaranteed to be simply 0. Okay, so now that promotes the idea of our squeeze theorem. The squeeze theorems now allow me to stay with the traditional method here. I'm just simply going to write the theorem down to make it a little more interactive here instead of showing that on a computer screen. But squeeze theorem says if we have some 3 functions, doesn't have to be continuous, and don't even worry about continuous or anything like that. At this point, we're only learning about limits, and we learned everything we could to handle a limit problem in case things became challenged like the one I just now show on the board. So if some function f of x and some function g of x and some third function h of x, all of them satisfy, so if the 3 function f, g, and h satisfy number 1, about f of x being trapped between, so greater than or equal g of x on the left hand side and less than or equals to h of x on the right hand side. So three function f, g, and h, or whatever function, but as long as you recognize, as long as we can recognize some inequality, some comparison, some trapping relationship like this, f is being trapped between g of x and h of x. And further, number two, and further that for some reason we can find out that limit of g, the bottom trapping function, when x coming to that limit point A is equals to the same limits of the upper trapping function h of x when x is getting close to A, and both of those agree to a finite limit L right here. So a lot of time throughout the rest of our lectures in calculus, anytime that I'm using a letter for indicating the limits, most likely they are the finite limits. So this is another requirement satisfying right here. Then once we have that second requirement satisfied, then the result guaranteed by the squeeze theorem is that the limit of the function being trapped in the middle here, if we are attempting to find that limit, we can save some effort for us. We don't need algebra technique, we don't need any fancy technique, because we know immediately that it should be also equals L as well. And so this is a result guaranteed by our squeeze theorem. Okay, and a theorem, by the way, a theorem is a truth that was proven by some mathematician in the past. So we don't have to worry about proving this. It's in the back of many standard textbooks out there, but here I'm just going to be simply showing you how you can apply this theorem effectively to get your work done, and to see how useful this theorem is going to be. All right, so after looking at the theorem, before I start into an actual example, just the essential understanding of this theorem only breaks down into two requirements. As long as you can meet number one requirement, as long as you can recognize that your limits, so supposedly, or I guess this function in the middle right here is the function that we're trying to find the limits. And so anytime you're trying to find the limits and you can recognize that your function you're attempting to find a limit is being trapped between some two other functions. So you're on your own to recognize these. So recognize these functions, and as long as you can find that inequality boundary here, and also if you can find out further that the two trapping functions g and h have the same limits L, as x is getting close to that limit point, then you don't need to find a limit for this. It's going to be L as well. Okay, and so here's how I am going to bring that into an example here. So let's now look at our actual example here. So as an example, and allow me to only introduce one example, and including the earlier introduction example, then that made two of them. But I will come back and throughout the course in later video lectures, and I will keep reminding everyone about how we can use this squeeze theorem right here. So, and you will keep seeing more examples of how squeeze theorems can be useful for us in terms of calculating the limits. But so here we just simply want to evaluate, and our limit problem here is how about e to the cosine of 1 over x. Ooh, looks pretty challenging. And then here we're looking at multiply with x to the 4th power. So x to the 4th multiply with e to the cosine of 1 over x. And now let's find the limits. Let's evaluate the limits of this function here as x is getting close to 0. All right, and so back to the squeeze theorem being written on the board earlier. So now I have to say it again. that the first responsibility is to be able to recognize. So our main function that we are trying to find, our target function is the x to the fourth times e to the cosine of 1 over x. So the first thing, when you're in the first step, when you're using or applying the squeeze theorem, we gotta make sure we can find. We gotta make sure we can find the. We gotta make sure we can find some trapping function, some pair of trapping functions that trap our function between. So I've had students, and it's at this point I have to admit, use as much algebra as you have to find this, because yes, playing with inequality is not always an easy work, but trust me, that there will be some point, there will be things that you have learned in your past will become useful here. And so, and in the end, as I always remind any of my students, you gotta have your algebra skills going before you can do calculus well. So how about it? So from my own experience, how about cosine? We can tackle that. Any trig function, either sine or cosine, actually, can be famously known to be in between an interval, in between a bound like that, anywhere from -1 to 1. But here it's a cosine function. All right, so hopefully everybody agrees with that. And so after we recognize this, and please, anyone being in this class for calculus must know this famous bound for cosine of x, or for cosine in general. And so now the challenge here is the next step right here. Our function here has e to the cosine, so cosine here is being the exponent. But for as a property of inequality, we can raise e to the cosine of 1 over x. And on the other hand, your left-hand side will become e to the -1 power. And algebraically, your right-hand side of the inequality will become e to the first power, which is e. And e to the -1 power is really 1 over e. So another equivalent step I could have written is 1 over e over, and being less than or equal to e right there. Okay, and so now, but at this point right here, look on the bright side, we're getting closer. Our middle function, but our function being trapped between these two constants. This middle function is getting closer and closer to the actual, is becoming closer and closer to the actual function. So the next step now, I am going to multiply the x to the fourth to my middle function. Now I'm making it complete. Okay, so now I'm completely looking at my main function right here. But this function now, once I multiply x to the fourth to that e to the cosine of 1 over x, then make sure we multiply that x to the fourth to the very left function. So now I'm looking at x to the fourth over e, and then on the other hand, I'm going to have e as a constant or a coefficient times x to the fourth. E is a known constant, is a known number. And so now this is how I can recognize that this maybe allow me to use a different color ink right here. But we can see this here as the g of x. And we can see this part right here as h of x. All right. And so now once we can recognize, and the question I keep having for from many of my students is that, does it always have to be this way? It doesn't have to be this way, as long as you can recognize some trapping pair, some pair of trapping functions that trap your main functions in between. But that's step one, but that's only halfway. The next step now is that we must, so when you're searching for your trapping function, you must also make sure that the next step now is, so x to the fourth, your over e, your g function right here. When you're taking this limit, as x go to 0, it gives you 0, isn't it? The rule of limits, the basic limit laws allows us to do this just fine. Notice e in the denominator here is only a constant. So limit laws allow you to get to that 0. No, e times x to the 4th power, when you take limits as x getting close to 0, you're also going to get to 0 simply by applying the rule of the basic limit laws right here. So you're not only trying to get any trapping pair of inequality, but you got to get some trapping pair of trapping functions so that it satisfies this as well. So the next step here is quite important as well. But then the way how I see this is requirement number 1 is being satisfied. Put a check mark there. Requirement number 2 is here, is also being satisfied. And so now, ultimately speaking, my limit limits for the entire problem x to the 4th times the e to the cosine of 1 over x. This function will now have limits equals 0. Okay? And so that is how we finish with our problem. Right? So from how it started, this is our function, and we work through the steps right here, and here's how we recognize our first inequality. And then second step, we've proven that the two trapping functions meet to the same limits. And now as long as we passed the two requirements, then for this final answer, we can just say that that function being trapped in the middle must come to the same limits. So before I close down this lecture right here, let me try to explain the squeeze theorem in somehow a graphical explanation. But a lot of time we can try to imagine that g of x is some function like this in blue. So this is g of x. Okay? And in red, I'm going to draw some h of x. So clearly speaking, with my drawing right here, g of x is above h of x. And we can think about our f of x as some function going up and down, but being between these. And so now x equals a is this limit point. So when we get close to that limit point, and as long as the two function in blue and in red, g of x and h of x, hits to the same limits, then the function f of x being trapped in the middle vertically has to also pass through that same limits as well. And so that's why we had that squeeze theorem as being written on the board.